Okay, this is a video answer key for the unbalanced forces and acceleration sheet. So we're focusing in on Newton's second law. So F net equals ma essentially. So that's going to be popping up. And all of these forces in this one are going to be unbalanced, which means there's going to be some form of acceleration. In each problem, you want to draw your free body diagram. And I might even suggest the component model of the free body diagram so you can get a sense of what forces are going in which direction in order to figure out where the unbalanced ones are. So this first one here, a box is being pushed across the floor. Now here's one thing, this box is being pushed, so this force applied is being pushed in this direction here. But when we draw our free body diagram, we don't want to draw the arrow coming in this way. So for example, if we were drawing a free body diagram, we don't want to have the arrow coming in like this, as seen in the picture, because that's not what really is happening here. We always start from the inside of our object, and we have the force going in the direction that it is actually going to be propelling the object. Now this pushing force here is actually going to be bringing it in this way, so we're going to have to draw it over here for our free body diagram. So here's my object. I'm going to start with my force. Now it's 32 degrees here, so when it comes down, it's also going to be 32 right here. So the Z pattern, the alternate angle. Like this. So if you can picture this, it's making that Z pattern right here of the alternate angle. So this is also 32. And this is going to be 78 newtons of force. Now, the floor is frictionless, so we don't really have any friction forces going down here. And we have our normal force because it's on the floor. And we also have our force of gravity as well. So this is kind of what the free body diagram looks like. But I'm going to convert this into a component free body diagram. And what I mean by that is I'm actually going to represent these different components. So like this X component and this Y component here of this force as separate forces on my free body diagram. So here it is again. If I look at all these forces here, I have this one is up, this one's to the right, this one's down, and this one's down. And I'm going to kind of ignore this, and I'm just going to look at the components. So the only force that I have going to the right is this one right here, which is the applied force, the force applied in the X component, and this one is the applied force in the Y component. So I'm going to have that here, force applied in the X, and the force applied in the X here is going to be 78 cos 32. So I'm actually going to put in the value for it right here, and that's newtons as well. And then for down, I have two forces. I actually have my force of gravity, and I also have my FAY, and then I'm going to have my normal force up here. Now it's being pushed across the floor, so there's really no movement in the Y direction. So if I think about my directional things here, I'm going to say that, you know, maybe up is positive and to the right, and this is negative and negative sort of thing. So there's zero movement. In a sense, the net force in the Y component is 0. So I don't really need to concern myself too much with these right here, because the only force that's really happening here is this one. So this is the only unbalanced force, and that's what's causing the acceleration. So in this case here, if I have, well, F net in the X is going to be equal to the sum of the forces. So really the only force that I have in the X direction, as I said before, is this one, which is 78 cos 32. And this is going to be equal to the mass times the acceleration. Now I'm trying to figure out the acceleration here. So acceleration is going to be basically 78 cos 32 divided by the mass, which is 12 kilograms. Okay, and when I put that in my calculator, I get 5.51, blah, 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 blah. But we're going to stick with our two significant figures. And this is the first question right here. Now, a couple of notes along the way. I might not have put units in all the times. I know I did for 12, I didn't here. For me, units as you solve is not as important as making sure that they're in the final answer. So that's really what I'm going to be looking for along the way. So therefore, I will ask you to do this. What is the acceleration of the box if the floor is frictionless? So you do have to write out a concluding statement. Make sure your concluding statement has your answer with significant figures. Now, I should say the one bonus to putting them in here is you might do what I just did and kind of recognize that, oh, I just put acceleration was meters per second squared, which is valid. It's kind of the same thing as newtons per kilogram. But I should probably put these as newton per kilogram because really that's what I was using in my problem. This is newtons, this is kilograms. So I might go ahead and change that just to make it more consistent with the units that I actually used in my problem. Okay, for the second problem, it's pretty much the same thing. The only difference is this one is being dragged or pulled across the floor, and there's an upwards force here of 34 newtons at this angle. So I've set up the same thing. This is my component diagram. If I look at all of the forces in the Y, I have my normal force and my gravity force, but I also have this, which I'm going to call my FAY, and this is my FAX right here. So the FAY is going in the Y component. Those are all going to cancel out because the sum of the forces in the Y component, or the net force in the Y, is equal to 0. So basically the force of gravity is going to equal the sum of these two, and I don't really concern myself with those right now. But the net force in the horizontal right now, because it is frictionless, is really just my FAX, which is 34 cos 32. So if I make that equal to the mass and acceleration, then I can find for acceleration by switching it around, and I get 2.4 newtons per kilogram forward. Okay, question 3 is a little tougher. It doesn't come with a diagram or anything, so you have to conceptualize what's happening here. So we have two tugboats. They're pulling a large barge into a harbor. So here's the barge right here. The first tugboat exerts a constant force of 1.8 times 10 to the 3 newtons, and that one's east 37 north. So I've already drawn kind of my east line. I'm going to make, since it seems to be going east here, I'll make east positive. And I may as well make north positive, just so I have everything. And it's gonna go, where is it, 37. So 37 degrees to the north. So it might look like something like this. And this is gonna be tug number 1. And then I also have tug number 2, which is east but 12. So it's gonna be kind of closer to this part here. That's 12 degrees, and this is tug number 2. It says calculate the acceleration of the barge, assume there's no friction action on the barge, and frankly, it doesn't even really matter because all we're doing here is we're trying to find out what T1 and T2 are going to be in terms of their components, and then use that for the acceleration in the horizontal component. So I'm going to divide each of these up. If you look at this, I kind of have my vertical component here and my vertical component of this one. And then I also have my horizontal and my horizontal here. So this part here, my little red line, is going to be T1x, and this is T2x. And then my green is going to represent my y. So this is my T1y and my T2y forces. There's really nothing else acting on it that is talked about. We're ignoring friction right now, so we really only have these forces happening, okay? Now, I am going to take this and I'm going to redraw it just with the components. It looks like if I ignore this on an angle, I'm just going to look at the components here. The only forces that I have up and down, so I'm going to kind of say north and south, is my T1y and my T2y. Now, because it's not moving north or south, it's going in a direct line, and it's pulling it straight, then what I'm going to do is I'm going to assume that those are equal. So my T1y and my T2y 2y are going to be equal. And I'm going to say the sum of the forces in my y component are going to be equal to 0. So those are kind of equal to each other. So I could say T1y is equal to T2y. And then if I look at the horizontal components, I kind of have two coming along here. I have what I'm going to call my T1x. And I also have my T2x. Now I don't really know, maybe my diagram's maybe not great because I don't really know which one's larger. I haven't put any thought into it at all. But I am noticing right now that my net force in the x is going to be the sum of these two things. So it's going to be T1x plus T2x. So that's going to be my net force in the x. And that's really where I want to focus on where my acceleration is going to be. Okay, so the one thing that you want to maybe stop and pause is this whole concept right here. Okay? Nowhere in the problem does it actually say that it was going in a direct straight line. So I'm just rereading this now as well. So it exerts, so it doesn't really say that. So I don't know, can we actually say this, right? So is this valid? Okay, and really the answer is no. We can't say that. We can't assume that they're traveling perfectly in a straight line because it doesn't say anything like that. So it's probably going to be traveling on a bit of an angle based on these tugboats. So we can't really do this. Instead, what we're going to have to do is similar to what we did with the y and say, well, Fy is going to be this plus this equals 0 in a way. Or no, sorry. Or can we do that? No, we have to add them up together. Sorry. So we're going to do Ty like this, and I'm going to add my T2y. And T2y is going to be negative because it's in my negative direction here, whereas all the other ones are going to be positive. Okay? So I have these two statements now, and I actually have all the values that I need to solve them. So I'm going to kind of solve them over here. So my fx, if I look at T1y here, I have my angle. I could use this angle as well. Like, now you could have gone in here and done 37 as well. That's totally fine if you wanted to do 37. The way I drew them, it might be a little bit different, but you can also look on here and say this is going to be the same as T1x and the same as T2x in terms of our diagram here. They're not necessarily equal. And this is going to be T1y and this is going to be T2y. So one of the problems that I saw on the test was kind of mixing up angles. So you might have drawn it like this, and then you're going to apply 37, but you can't do that, right? Because this is actually a 90-degree angle, and if 37 is right here, then this would have to be 90 minus 37. Okay, so 90 minus 37 is 53, so I could put 53 here. And same with this is 12, but I could also put 78. So you have to really focus in on where are you drawing your components and then make sure that you're representing them correctly. So if I'm going to use 53 and 78, then I need to make sure that for F, it's going to be, sort of across here, it's going to be sine. But if I use this one, it's going to be cos. So it's either cos 37 or sine 53. And I have to be conscious of which one I'm going to be using here. Both of these are going in the positive direction for x, so they're both going to be positive numbers as well. Okay, so I've gone through and I've kind of found out what my net force in the x horizontal component is and in the y vertical component here, and kind of showed my steps on the way down. And now what we have to do is we have to put it together to see our actual resultant force here, so our overall movement here. And we're going to use Pythagorean for that. So if I look at these two things here, I can kind of see that it's going, let me see here. So 2000, let's say, I'll do it in red, I guess. So it's kind of look like this. Let's say 2009, 14 newtons this way. And then we're going to go up 8, 12, 98 newtons. And therefore, the actual path of this, which is the path of the actual barge itself being pulled behind these two, will look like this. And this is where we're going to use Pythagorean for our F net. Okay, so our F net is going to be the square root of the squares of the components here. And I'm just going to put these in. When I put all these in and get it, I'm going to get to 2,828 and 49 newtons. So now I have my net, and what I need is I need to figure out my acceleration, because that's really what it's asking for. So my acceleration is going to be equal to my net force over mass. My net force is 49 newtons, and my mass at the very top is 4,200. You could keep this in scientific notation if you wanted to, but it's not that hard for me to convert it. That's about 0.67 newtons per kilograms. And the last thing we need here is we need to know this angle right here, because we are dealing with acceleration, which is a vector. This is just the magnitude right here. But we actually need the arctan to figure out this. So this is just my 812 number, really small here, 2709 14, and that comes out to 16.7 degrees. Now, if I look back up into my significant digits, I haven't really been keeping significant digits. I've been trying to keep a little bit extra because I've been using numbers and reusing numbers, but I can see that really it's 2 here. So it's 2. And so in my therefore statement, this is where I want to make sure I have proper significant figures. I'm okay if you don't have significant figures in the final answers, but in your final statement, it needs to be proper. And so in this case here, the acceleration is 0.67 newtons per kilograms. And then we have our direction, which this is going to be 16.7, so basically 17 degrees. And it's going to be east 17 degrees north. That one was pretty involved. Okay, so now we're going to get into more of a inclined plane sort of thing. So one section of a roller coaster involves cars and passengers sliding down an incline before going around a vertical loop. The incline is set up at 36 degrees to the horizontal. So if I kind of draw this, here's my incline at 36 degrees. So it's kind of going down here, and then it's going to swoop up and go into its little vertical loop. But I'm not concerned with that right now. I'm only concerned with this portion of it. When I draw my free body diagram, which is going to basically involve my cars and passengers all together, it will be on this incline, and we have to talk about some forces that are acting on it. Now, friction is negligible. We always are going to have gravity. So this is my Fg, and we're going to have our normal force as well. And that's pretty much it. There's nothing else going on here. This is just a gravity coaster. So I will have my two components here and here. Now, unlike what we did before where it's XY, 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 we're going to call these something a little bit different. We're just going to kind of take our system and rotate it slightly so it looks like it's on the X and the Y. And you could even redraw this if you really wanted to. But this one here is going to be our FG perpendicular, because it's our component of gravity that is perpendicular to the incline. And this one here is going to be our FG parallel because it's the portion of gravity or the component of gravity that's parallel to our incline. And that's really going to be what's bringing it forward. So if I'm going to just draw my quick little free body diagram, not on an angle, I have my normal force kind of balanced out by my perpendicular component of my gravity, and then I have the parallel component, which is really what's going to be the unbalanced force that's bringing this forward. Now, in this case here, I can say that the sum of my forces in my y are 0, so I don't really need to concern myself with those. But when I'm talking about my x here, this really makes up the sum of my forces in the x, or I guess what we can call, we'll call it x in quotations, which is really the sum of the forces in the parallel version. And this is kind of like my y, which will be like the sum of forces in the perpendicular sort of thing. So that kind of all is the same thing. We just kind of shifted our little coordinate system a little bit. So that's what I'm going to be dealing with. And this is really equal to, if you look at this angle again, this is 36 right here. So it's going to be the sine here. So FG sine 36. So I'm going to have is going to be my main force here, okay? Okay, so if I'm talking about this is equal to the mass times the acceleration, I'm going to have Fg, which is really just mg sine 36, and that's equal to mass times acceleration. You're going to notice that mass will actually cancel out. So if you were concerned that mass was never given, it just goes away magically. And so the acceleration is going to be equal to basically g times the sine of 36 here. So g, we're going to say 9.81 newtons per kilograms sine 36. And that'll leave us with our acceleration. Okay, so when I do that, I get 5.766, say newtons per kilograms. And this is forward or down the hill or whatever. If you put 9.8, you might get 5.74 and then round to 5.7. So just be aware of that. It just depends on the value you use for your G. But the answer here is based on 9.81. And so that's the magnitude of the acceleration of the cars down the ramp. We don't actually need the direction or anything like that because it just asks for magnitude. And that was one of the things on, I think it was a previous quiz. When it says magnitude, don't go calculate the direction. That just is inefficient. Okay, so therefore, of the acceleration is, and if I look here, 36, so I only have two significant digits, so I'm going to say it's 5.8 newtons per kilogram. Okay, for this one here, similar to one that we did in class here, we are assuming that the surface of the ramp is frictionless, and the pulley is frictionless. We'll always assume that the rope is massless. And so what's going to happen here is we're going to have some movement here. So block A has a mass of 4.2 kilograms. A string passes over a pulley to block B, which is 1.8 kilograms. And we want to figure out the acceleration of the block's end tension in the string. So there's a lot of things going on here. We have friction. It's kind of like our example that we did in class, except this one's also on an incline. So we got a few things going on here, okay? And so that's where it gets a little more complicated. Okay, so a couple of key ideas here. We're using one rope between, so as discussed in class, the tension will be the same all the way along here and here. So that doesn't seem, so that's one of the things that will be shared by both the blocks. The other thing is this whole system will accelerate at the same rate. So the acceleration of mass A and mass B will actually be the same as well. What we do want to look at is each block kind of separately. So I'm going to draw free body diagrams for each of them. So here's my mass A right here. And mass A is going to have our force of gravity coming down, which is really just mass A times G. And then we're also going to have our tension force. And this is our tension, which is basically B on A. It's a reaction, action-reaction pair. So we have that happening right there. Block B is a little more confusing. It's on a slant, so people might not really understand about the angles and stuff, but all we're gonna do is we're gonna kind of look at this angle and we're just gonna pretend that it's a flat surface like this. Although we are gonna be pulling up against gravity as well. So we have to be aware of that as well. So when we draw all of our little things for mass B, just remember that we're gonna have our normal force right here, and we're gonna have our force of gravity kind of going straight down here, and then we're gonna have our components as well. Okay, now it is frictionless, so we don't have any friction going the other way. And let's see, is there anything else there? No, I don't think so. Okay, so this is the FG perpendicular, and this is the FG parallel. So I'm gonna draw mass B just in the orientation that I am more comfortable with, which is not on an incline. But if you kind of look at it, it is on an incline, but just kind of tilt it so it's not, like this force that's extending right here is the force of tension, right? And so that one is going to be extending. And then we have the normal force right here, which is balanced out by the force of gravity perpendicular. Then we're going to have our force of gravity parallel, which is kind of bringing it down the ramp, but then bringing it up the ramp is going to be the force of tension, and this one is going to be A on B. Okay, and those are action-reaction pairs. Okay, so these ones here are action-reaction pairs right there. So we have our diagrams here, and you can look at each diagram separately and come up with two equations, because on both diagrams we have our tension force, which will be the same on both things, and on both we're going to have acceleration, which will be the same in both as well. So I'm going to set up equations for these here. For this one here, my acceleration will likely be downwards, so it's going to be accelerating downwards. This one's heavier, so it'll probably go down and pull this one up. So probably this one will be larger. So if I'm just thinking about how I want to kind of set up my grid here, I'm going to say that down is going to be positive, and kind of to the left is positive, and then up is negative and negative. And it might mess you up a little bit, because this looks like it's kind of going up to this way right here, but we're really just looking at this as a diagram here, and so it's going to be positive and positive, negative and negative. So the way that you set up your coordinates is really, really helpful. We're going to set up systems of equations here. So if I look at mass A, I'm going to have my net force on block A is going to equal my FGA, and then plus my tension force. But my tension force is going to be negative. So I'm adding them together. The net force is really the sum of the forces. That's what it is. But we have to remember direction. And because my tension force in this direction is going to be negative, then I put it in like that. Okay. Now this is going to be equal to mass times acceleration, and this is once again the mass of A times acceleration, which is what we are looking for. And FGA is mass of A times gravity minus the tension force, mass of A times acceleration. Now I cannot cancel the mass of A right here, because I still have this little FT, or tension force. Okay, so this is one of my statements right here. I'm actually going to kind of flip-flop this and make sure my FT is on one side. So I'm going to say that FT, if I put it over here on this side, it becomes positive. And I'm going to put this on this side. So it's going to be MAG minus MA acceleration. And this here is going to be my equation number 1. Then I'm going to look at this for my equation 2. Now I'm not really looking at the y components because my normal force and my perpendicular gravity force are going to cancel each other out. And so which way is it being pulled? Well, it's getting pulled this way up here. So it's going to kind of be moving in this direction, which is my positive direction. But my net force that I'm concerned with in block B is going to be my tension force plus the FG parallel, which is going to be negative, and that's going to be equal to my mass of block B times acceleration. And remember, acceleration is the same in both of these scenarios, and so is FT. So I have FT minus, this is going to be the mass of B, and then parallel, if I look at parallel, it's going to be sine of 32, and that's my MBA, like that. And I'm just going to have it so I can write it for the FT right here. So the force of tension is going to be my mass of B times the acceleration, adding my mass of B sine 32. And this is going to be equation number 2. Now I'm going to make 1 equal to 2 here. So I'm going to say mass AG minus MAA equals MBA plus MB sine 32. And I realized I forgot my G here, so I'm going to squeeze my little G in here and here and here as well. I think I'm going to have to add a little piece of blank paper here because I'm still going. Okay, so I'm going to sub in some of the values. I'm just going to move over here because I need some more room. Whoop. So I'll go here, and I'm going to plug in some of the values that I know. And I want to eventually get down to A. The other thing you could do if you wanted to is you can kind of move things around so that A is all on one side, and then you can just kind of solve for that. So I actually might do that. I'm noticing that this one here and this one here both have A in it. So I might move all the stuff with A's over to this side, and then work from there. Okay, so I'm gonna write this as MB times the acceleration plus MA times the acceleration. So I'm going to put all that stuff on one side, and that's going to equal MAG minus MBG sine 32. Because then what I can do is I can factor this out, and then divide both sides. This is not something you have to do if you find like, man, I'm just working with symbols and stuff and I would rather just plug some numbers in. Then you can, but the benefit of this is that you're going to be really precise in your answer because you haven't really lost anything through rounding along the way. All right, so I'm going to plug in my numbers here and generate my final answer. Okay, so I just pumped in the numbers here. When I put all the numbers in, I get down to 5.3. Newtons per kilogram, meters per second squared, chickens, whatever, what's that saying? I don't know, tomatoes, whatever. And then I'm gonna sub that value into number 1 and I get 18.9, so pretty much 19. So when I get down to significant figures, then my answer is acceleration and my tension force. Okay, for the final question, I mean, it's kind of like the tugboat question a little bit, but now we're pulling it upwards. So unlike the tugboat question where we didn't really have any drag, we actually do have a little bit of drag going downwards. We have the force of gravity now, which is going to change things a little bit. So it's kind of like the tugboat question, just the next level. So I've drawn 2 free body diagrams. One is just with the actual angles and stuff like that here. But then the other one is just showing the components. So it kind of shows you just the vertical and horizontal. I'm not really sure which way it's going to go, so I'm just going to kind of say that north and east are going to be my positive, and south and west, or I guess I should say up and down, technically. So I'll say up and down, sorry. And then east and west, sure, right and left, forward, back, whatever you want. So I'm going to kind of keep those right now, and then I can define them as I go, because it doesn't really make it clear if it's east or west or forward or backwards or whatever. So I'll just stay with that. Looking at this diagram here, there's a couple things that I know. I'm assuming it's pulling up. It says are lifting a car, so I think it's going upwards. So chances are these are going to be bigger than the force of gravity. And it's lifting them onto a cargo ship. The car has a certain mass, so the mass of the car is, where is it? 9.50 times 10 to the 2 kilograms. If you don't want to deal with significant digits, that's 1, 2, so that's 950 kilograms. It's not that much, actually. It's a pretty light car. And there's two cables here. So we have T1, and they actually equal each other. Both of the tensions equals 2.00 times 10 to the 4 newtons. And so 1, 2, 3, 4, that's like 20,000 newtons if you prefer not to deal with scientific notation. It's up to you if you like it or not, but that's one thing you can do at the very start. The other thing I want to check at the start is I just want to make sure that all of my units here, kilograms, newtons, like they're all in standard units, so that I can just kind of continue on with my normal ways. And I don't necessarily have to put units in as I solve my question. So these are my two statements here. I have my components of my x, and I can see that there's two things here. Since I denoted going east as positive, then I'm going to pick this one first and say, well, this minus that essentially, or another way you can think of it is I'm just adding them together. It's this plus this, but this one's going to be minus because it's going in the negative direction. In this one here, my FG is going to be minus or negative. So that's why I added these two and I subtracted this. And that's kind of my setup. Once I've set that up, I have to kind of figure out, well, what are these little trig ratios going to be? So if I look at T2x here, I can see that it's going to be T2 and then cos of 40. And I'm going to subtract T1 cos of 30 right here. Now, T1 and T2 are the same, right? So since these are kind of the same, I can pull them both out and I can say something like, well, T1, and then it's just the cos of 40 subtract cos of 30. I don't really know if that helps me or not. And then this equals m acceleration here. So mass times acceleration. And so what I'm going to do is I'm looking for the acceleration. So that'll be this divided by the mass, essentially. Now, I have the mass and I have the tension, so I can kind of find acceleration of my x right here. So T1 is 20,000. I'm multiplying it by cos 40 minus cos 30, and that's all divided by the mass of the car, which is 950. So I'm not really dealing with units right now. I'll deal with those later. And I can crunch those numbers later. Now I'm gonna set this side up here. So T1y, if I look at this right here, it's gonna be T1 sine of 30, and I'm gonna add T2 sine of 40 and then subtract mg. And this here is mass times acceleration. So same thing as before, T1 and T2 are the same, so I'm just gonna pull out T1 just so it's there. And then I can say sine of 30 plus sine of 40, and then subtract mg. And I'm gonna divide that all by the mass of the car. So acceleration is 20,000 sine of 30 plus sine of 40. And then the mass is 950 times 9.81. Try to fit it all in. Ran out of room here. And 950. And then I can crunch those numbers as well to get my acceleration. And this is my acceleration in the y, I should specify. And this is my acceleration in the x direction. Okay, so assuming I put all this in my calculator, right, I got an acceleration in the x component of negative 2.10, which means it's kind of going to the left, or what I've denoted as west. And then acceleration in the y is going up 14.25 newtons per kilogram. And so now what we have is we have those components. So I know it's going to be up 14.25. It's going to be over 2.10, whatever, newtons per kilograms. And then, so the actual movement is kind of like this. Okay, so that's kind of what I'm looking for here. So I can use my Pythagorean theorem now to kind of find out my total acceleration. Okay, so when I got that, I got 14.403 newtons per kilogram. So looks like I have maybe 3 significant digits. Sometimes what we do is when we look at significant digits, we look here, there's 3. This one has 3. In the diagram, the angles only have 2, but we kind of ignore that. We ignore the angles. We kind of assume the angles are really precise. And I'm going to stick with 3 here. So 14.4. Is what I'm going to say. If you said 14 and argued that it was the angles, like, that's not a huge issue. But we do need to find the actual direction as well. And so I'm going to look at my little grid here, and it's my inverse tan, and I have 210 over 14.25 here. Inverse tan. I get 8.48 basically. Okay, so that's my angle right there. Now, usually we don't really use that angle like from up, so we might have to look at this other angle right here. And so this angle will be 90 minus, let's say, 8.38 or whatever. So I get like 81.6 degrees sort of thing. So I can say, well, therefore, the acceleration is 14.4 newtons per kilogram or meters per second. And we're going kind of like, I don't know, 82 degrees above the horizontal. Okay, so I'm going to keep my units for my angles at 2, and I'll keep my other ones at 3 moving forward. And that's kind of the answer to the last one.